All right. Normally, I would never teach indeterminate exponential forms as the first lesson back after break. That's crazy.
We're just that good.
But you are just that good.
Oh, I don't want to.
By the way, sorry, one more thing about overview. Sorry, you guys are so yappy on the lesson. We'll get through, obviously, the end of the book this semester, and it'll be in about mid-April or so. At the end of April / first weekend of May, on a Friday afternoon, a Saturday, or a Sunday, you will choose one of those days to take my final. My final is in BC Calculus exam. Thank you. Okay? That, whatever you were on that will be your grade in the final. I will get that back to you, and you'll have another week or so to go over what you missed in terms of preparing for the actual BC Calculus exam. At that point, I hope you'll say, man, your exam was a lot harder, and you'll smoke the BC final. You'll get July 5th, you'll get your results back. You'll say 5. I don't even need to open it. And I'll be all happy, and my kids will be okay. I'll say this also. I have, in 8 years, I have never had a perfect score. Never. Okay, now that said, that doesn't mean... Actually, there are usually about 200,000 people that take the BC Calculus exam. And out of those 200,000, about 200 get a perfect score. It's very, very rare.
But 200 is still a lot.
That still sounds
200 out of 200,000, what percent is that?
Oh, not percentage.
Thank you, Mr. Scott. Okay, so I actually believe that you can get there. Now, if you get that perfect score, my word to you is that I will come and get your your best possible picture. I'll go to Costco and get it blown up to 3 foot by 5 foot. And I'll put it right there. And I'll put best student ever. Right there. And I'll keep it up until I retire.
See, that's motivation. That's actual motivation.
So get that perfect score. We'll be there perfect too. All right. Okay, so I normally start with my review, but my review is tomorrow because my review, which I really like, has set 111 on it, and I didn't get to teach last semester. Got kind of away from me at the end of the semester, and I didn't teach 111. So I need to teach 111. Tomorrow we'll review the most recent 7 or 8 really BC topics. So we can get rolling with the new material, all right? I'll just tell you right away that BC Calc, or the Calc 2 basically, is not a lot like Calc 1. Calc 1 and Calc 3 are very similar, just two variables versus multivariates. But Calc 2 is very different. So start from scratch. Those of you that killed it last year, you're going to have to improve yourself again. And those of you that didn't kill it last year, it's a fresh beginning. So here's the deal. Indeterminate forms. When I talk indeterminate forms, I'm talking about a limit that you're not sure how it's going to come out. It usually involves infinities and zeros. Now, the first 2 indeterminate forms are when you have 2 functions in a fraction form, and both of them go to infinity. Now, that could, I don't know how that comes out. It would be a total third grader kind of thought to say, well, that must be 1 because they're the same. We know that it's about how they approach infinity, whether the top approaches faster, the bottom approaches faster, or so on. So you have to go into how fast do they move, which means we take derivatives, and that's why we do L'Hopital, right? Same with 0 over 0, approaching 0 over approaching 0. How that comes out kind of depends on how fast they go to 0. Indeterminate forms, part 1 was these 2. We use L'Hopital straight up, right? Okay, the next were 2 indeterminate forms where you're approaching 0. Remember, these are approaching, not actually 0. Approaching 0 times approaching infinity. A small thing times a huge thing. Well, it might be huge if the infinity wins. It might be 0 if the 0 wins, or it might be somewhere in between. But I can't really know. And it's very common error for the first few weeks. People start saying, well, if I don't know, I want to look at the derivatives. But remember, if you take the derivatives here, you're just taking the product of their rates of change. Well, what does the product of the rates of change tell me? That doesn't tell me anything. What tells me something is how their rates of change compare to each other. This is a comparison of the rates of change. Multiplying the rates of change doesn't tell me anything. You know what I mean? So the next step from here is to make it a L'Hopital case. You make it a proportion case, some kind of fraction. Usually means making it some ugly fraction. But you've got to make it a ratio so you can compare the rates of change, not multiply the rates of change. You with me? Same goes here. Infinity huge minus huge could be a lot of different things depending on how fast huge and huge happen. But again, I need to compare the rates of change so you make it a quotient. Okay? So these are indeterminate, but you need to make them a quotient before you lose L'Hopital. Cool? Are you with me? Okay. Now, there are altogether then 4 we know and 3 more today. 7 total indeterminate forms that one must know. This is the last day of indeterminate. The indeterminate forms we're going to do today are all exponential in nature, approaching 1 to huge exponents. Now, depending on how fast it approaches 1, how fast it approaches huge, could be a lot of different things. Could be e. Actually, e is a form of 1 to the infinity. 0 to the 0 feels like it's not even indeterminate because, hello, there's zeros all over the place. It should be 0. And yet I'll show you that it actually could be a lot of different things. And then infinity to the 0, huge to small, that also, most people see how that can be indeterminate. But the first thing I want you to do is get a feel for what the numbers of this look like before it just amounts to symbol pushing, which it will be a lot of symbols and analytical. I'd like you to see some number cases in this to show you what's going on numerically. So say I wanted to show that 0 over 0 is indeterminate. I'm going to try and show that this could actually come out a couple different ways based on what's going to 0 and how fast. I tried to choose 2 numerical cases that behave differently. And I'm going to take a linear base to an exponentially changing exponent and then switch the 2 and show that though they're both 0 over 0 kind of in nature, they come out 2 totally different ways. So I'll get you 1 together and then maybe you'll investigate these 2 on your own here. So say I went to 0 in a linear, quasi-linear kind of way. Something like 1/2. Now I know this isn't linear, but I'm thinking the denominators are linear. Do you agree that these bases are definitely going to 0? Okay. Now, but pretty slowly, relatively speaking. Exponentially, I want to go to 0 even faster in the exponent. So say maybe something like 1, and then 0.1, and then 0.01. Let's see what those, now surely that's 0 over 0, because the exponents are also approaching 0. But for these numbers, how do those come out? Well, that's where you need to get out your calculator. Feel free to grab your calculator. You'll need it for this part. And tell me roughly what each of those equal. I don't need a calculator for the first one. That would be enough for that. My outcomes are looking closer and closer to 1. If I went 1/5 to the 1,000. Yes, ma'am. Yes, sure. What do you want? Inspire or E4? Inspire. So you get something like that. Look. What does it look, ballpark? We could go further, but what does it look like they're approaching? Yeah, it does look like they're approaching 1. Okay? Now my goal is to show that that's not always the case when you go 0 to the 0. It could, based on how they approach, be something else. So say we went the exponential, or the base was exponentially changing, and some form of the exponent is linear. So maybe something like 0.1 to the 1/2, and then 0.01 to the 1/3, 0.001 to the 1/4. Could have just switched the two. I don't know why I got. I made things so complicated. Okay. My results look like that. They're definitely, well, I'm not sure if they're approaching, I think they're approaching 0, but they're most definitely not approaching 1 like those are. We agree these are getting smaller. My point then is that because these are not equal, 0 to the 0 is not always the same. It's indeterminate, or it can't be determined until you get into it a little more. So approaching to 0 to the approaching 0 could be a lot of things. Here I have a typo. Sorry, I said exponential linear and exponential linear. I meant to switch those and approach this in 2 different ways. Okay? Would you try doing something like that? We don't exactly have to have the exact same numbers, but your goal is to show that you could approach a huge base and approach 0 in the exponent 2 different ways and get 2 totally different outcomes. Okay, so do you feel like you know enough of what I'm talking about to try that one on your own? Okay, try that one on your own, and your goal is to verify that infinity to the 0 could come out a couple different ways. I know they shouldn't. This is what I got, but somebody in the last class had a better idea. They did 100 to the 1/2. Why is that an easy one? Yeah, because that's 10. And then they did 1,000 to the 1/3. And hey, looky there. Isn't that 10? So I thought that was really clever. I didn't even think about doing that, so that's one way to do it. That then definitely seems like, in that case, results are always approaching 10. Practically nothing. I don't even need to look at that. What are those approaching? Fractions to, what if I took 1/4 to the 10,000th power, a fourth of a fourth of a fourth of a fourth of a fourth, that's approaching 0. Yes, sir?
Isn't the linear supposed to be increasing now and the exponential supposed to be decreasing, going to 0? Because infinity to the 0. And on the left side, but on the right side, you're
On this side.
Yeah. So
Oh, gotcha. You're right. Sorry. I was thinking I could just switch those 2, but that was when they were both going to 0. Sorry. Absolutely right. Thank you. So I need to make this huge 2 to the 10. Thank you. You're right. I'm really rusty. Okay. So that I still think I know what that's going to be. Think about that without your calculator for a second. 4 to the 1,000th power. What does that mean? What's a 1,000th power mean? Yeah, doesn't that mean, isn't this the same as the 1,000th root of 4? Or what times itself 1,000 times equals 4? What would that have to be like? Small. 0 small?
No, like,
Why not 0 small?
because then you get smaller.
Then you get smaller. So it has to be above 1. 1's a great dividing line for exponential behaviors. Okay, so it's got to be really, really close to 1 so that it gets bigger, but really slowly. Yeah, so there's some like 1. Either way, however, they're both infinity to the 0 or approaching infinity to approaching 0 cases, but they come out very different. And so again, it's indeterminate. Okay, I'll let you do this one on your own, but I'll remind you the most famous of this case, this one we did last year, isn't the idea of that. I hope that's familiar. What is it? Yeah, it's E. The bottom, the inside definitely goes to 1 because this goes to 0, so that approaches 1. But the exponent gets infinity large. And that play between trying to be 1 but trying to be infinity, it actually is somewhere in between. And so E, you'll see then that this could be a lot of different things too, depending on what you got. But it'll often involve E. All right. Now, that's the first part. Is I wanted you to see these new forms. Why are they indeterminate? Right. The next thing I want is, this is the skill I definitely did not do a good enough job on first semester, and that is the next thing you have to do is determine, is it indeterminate or not? Do I use L'Hopital or do I just know the answer? There were cases in this first semester where people were doing cases that amounted to this, and they were doing L'Hopital. Now, is that, I wonder what it is? I mean, can any total fourth grader tell me what that is? That's freaking huge, right? That's not indeterminate. There's no I wonder what it's going to be kind of thing to this. It's I know what it's going to be, right? So my next thing I want to work on is determining, is this indeterminate or not? Or can I just know the answer without all this work? It's important that you save yourself all this work if you can, right? These are the 7 indeterminate forms. I'm not big on memorization, but you really do need to have these down in your brain. The first 2 I'm sure you already do. I don't know about the second 2, and the next 3 are new, so gradually they'll get into your brain. But these, not every collection of infinities and zeros is indeterminate. All these are something, not indeterminate. For example, small positive, we'll go positive. Small positive divided by huge positive. What is it? You took a small number and divided it, small number, and then divided it into 1 billion pieces. How big is each piece? 0. Okay? That's not indeterminate. Okay? Take 1 billion centimeters or whatever, and then break it into pieces that are 1 billion big. How many pieces do I get? If you take a huge number and divide it by something tiny, what do you get? Big. Okay? If you took a small number times itself millions and millions of times, a tenth times itself 1 million times, what does it approach? 0. That's not indeterminate. Okay? It's 0. We already talked about infinity over infinity. Anybody knows that's infinity. Infinity plus infinity, hello. Infinity, and negative infinity minus infinitely large is obviously not indeterminate, okay? So have your eyes open and don't just assume mindlessly that, okay, think first. Now, I'm going to start to ask you to show your work a little differently because AP is on this recent vendetta against what they call showing bad work, although every professor I ever had showed it this way, okay? They are violently opposed to next to a limit saying this is 0 over 0. before you do L'Hopital, because in their argument, I guess, is that doesn't mean anything. 0 over 0 doesn't mean anything. I agree, that's why I'm going to investigate further, but they don't like you to even write it there, okay? So instead, we will no longer write it that way. We will instead show each of the pieces separately. Sine of x goes to 0, and x goes to 0. So by L'Hopital, I show that the derivatives can be used, okay? This, actually, we know that one's already one, so I don't even know if I do L'Hopital. But this, rather than 0 over 0, needs to be your new modus operandi, okay? We need to do it that way. So, as an example, on all these problems below, you're going to determine, is it indeterminate or do I know the answer? So, say you had the problem as x goes to 0 from the positive side or the right side of x natural log of x. You will show each of the two pieces and what they do. Natural log of x goes to negative infinity and x goes to 0. When I put those two together then, 0 times negative infinity is in fact indeterminate, yes? That's, at this point then, that's all I'm going to do and I'm going to stop. It's indeterminate. We'll talk in a second about what we do from there. So if the problem looked more like this, you look at each of the pieces separately. Cosecant goes to infinity, 1 over x goes to infinity. Infinity to the infinity is not indeterminate. That is actually infinity. So in this case, if it's not indeterminate, you'll tell me what it actually equals. Try it on your own. These, we'll just do these 3. There's lots of them actually, I have 12 of them, but I'll have you do these 3 on your own. Show each of the pieces and what they do, and then decide if it's overall indeterminate or do you know what the answer is. Oh, I thought you were just saying that. No, you do not. I can just say that.
It goes to 0, yeah, there we go. Oh, right.
All right. For number 1, natural log goes to infinity. X goes to infinity, and infinity over infinity is indeterminate. Do we agree? Okay. For number 2, 1 over x goes to infinity. Natural log of x. If you need to look at the graph, it helps me to look at the graph. Natural log of x goes to negative infinity. What's infinity minus negative infinity? Is it indeterminate? No. No, it's infinity. That's your answer to the limit question. Okay, your answer is done. What about as x goes to 0? What does tangent of x approach? What does natural log approach? And Is that indeterminate? It is. It is one of the indeterminate forms. Okay. You understand what you're doing in this section in terms of deciding if it's indeterminate or not? Okay, there's another 9 on the back side of that. I'll let you do it at your leisure. That'll be part of your homework. Let's jump to the next section. Okay? The next step then would be after you've decided, yes, it's indeterminate, then you go forward and determine what's the limit. So let's talk about that in the new types of problems. You're still going to show that is it indeterminate work separately and saying, all right, it is indeterminate, but now you're going to go further, right? Let's talk about how to find what is the limit on those new exponential forms. It's kind of logical, but if I need to investigate these exponents further, then it might be better to have them brought down. And how do I typically bring exponents down? Logs, yes. I can, these notes are a little bit, I wish I would have done one step here. I should have had one step in here. So, say for example, I had the limit as x goes to 0 of x to the sine of x, which is a classic problem in most textbooks here. Okay, x goes to 0 and sine of x goes to 0, so it is one of those 3 indeterminate forms. All right, 0 over 0 is one of those forms we talked about. Now we're going to actually find the limit. Your first goal will be to try and bring that sign down. You can't do that unless there's a log there. But you can't just say, hey, I feel like putting a log there. That's not mathematically sound and just change the problem completely. We have to keep it balanced. Now we know that there are 2 ways to balance something you want to do. If, for example, I had something that was true, I could change that equation one of 2 ways. I could do the same thing to both sides of the equation, and I have not changed the problem. It's still true. Yeah? Likewise, you could also do an undo to one side. I think you'll agree that if I took 2 and subtracted 2, that also would maintain truth. Doing and undoing with its inverse, that's also allowed. When you have an expression like this, it's not really an equation per se, it's an expression, then you really have to do the undo and the do and undo kind of approach to this. I want to use logarithms to bring the exponent down. To undo that, I'm also going to have to exponentiate that. Now, what I'm not showing here, I'm kind of skipping my first step, but if I do that then, I'd say this is equivalent to if I took e to the log of x sine of x, yeah? Are you with me? I mean, if I simplified that, am I not right back where I started? Follow? Okay. Now, this is the part that people in the last class had a bit of an issue with. That e doesn't necessarily have to be thought of as inside the limit. Think of this in terms of order of operations here. If I said this, then really, don't I just need to know what the function part of that goes to? And the 3 is constant. It's just going to do what it's going to do. But the function, isn't that mean then that I really need to figure out what does the function part do? And then I'll exponentiate that once that exponent's been figured out, yeah? Are you with me? Are you with me?
Yeah.
Okay. So in terms of order of operations, you know, if you were to do a pre-algebra lesson, you know, order of operations with limits thrown in, limits are actually could happen in a lot of different places as long as they happen before the function's there, okay? They have to be done on the function. I definitely couldn't say this is equivalent to 3 to the x squared minus the limit of this. Obviously would be total garbage. I couldn't throw the limit in there. The limit has to be done on the function itself, but in terms of any constant, it can be brought up front. You with me? Are you with me?
Yes.
Okay, I understand you're rusty, but give me some life here, people. Give yourself a little, whatever you got to do. Okay? Now, my point then is this. I'm going to exponentiate at the end. I need to figure out what does this exponent thing come out to be, and then I'll e it at the very end or exponentiate at the very end, which is to say I'm going to e later and focus on the function. E is a constant. Remember, it's just like 3 behaving here. Okay, now with log rules, I can bring that sine of x down. you'll see that this is still indeterminate. What does sine of x go to? 0. What does log go to? Negative infinity. It will never be the case that this is indeterminate, but after logging it's not indeterminate. That cannot happen no matter what. If you take one of these cases and do the log rule on it, it's always going to stay as another indeterminate form, whether it be that or that or that. If it's indeterminate in its exponential form, it's going to be indeterminate later too. And thankfully, you don't have to continuously show still indeterminate, still indeterminate. You don't have to do that. You just keep plowing ahead with your going to L'Hopital, right? You with me? So I don't need to, for you to here show me, hey, look, this is 0 to, I don't need to see. You with me? Okay, instead you say, all right, I know this is still an indeterminate form. I need to get it to the point where I can compare the rates of change, which is to say use L'Hopital. So you need to make it a fraction. This is going to be awkward in many of these cases. Making that fraction is going to be really making it worse, it feels like almost on one level. And that's just part of these types of problems. It's actually going to feel like complicating it to put something in the denominator, but it's what you got to do, okay? So I put the sign in the denominator. You practically never put the natural log in the denominator. It's almost always going to stay in the numerator. I took my derivatives, so that's where I'm at here. You following with me so far? Any questions? Okay, this is the second skill of L'Hopital that I don't feel like I got across very well first semester. You need to have in your toolkit cleaning up cleverly so as not to waste your time. For example, if I rewrote this as sine tangent over x, many students, in fact, I guarantee you most students would probably say, oh, 0 over 0, here I go again, and L'Hopital again. And the bottom would clean up fine, and the top with a product rule would be okay. But it's actually not necessary if you have your eyes open a little bit and think in different ways. This is going to come with experience. For example, rather than do another set of derivatives here, or L'Hopital again, I busted this up into sine over x and tangent, and then just found each limit separately. What's sine of x over x? 1, and that goes to 0. And so it bypasses all that product rule stuff. Just don't get locked into, okay, 0 over 0, do L'Hopital again. There's sometimes some cleanup to be done to make your life easier if you just have your eyes open a little bit. At the end of the day, then you get 1. Here's where I anticipate, having taught this class 8 years, it's always the same fight with students every year. Okay, 1 is a very common answer. In fact, I would say for these problems, you'll get 1 probably 95% of the time. Okay, and so it'll be very much the case. Within a couple days, I'll hear a student saying to another student, just put down 1. It's always 1. Okay? And then, what do I have to do? Well, then when I give you a test, I have to search for questions that don't come out to be 1 to get you, to penalize you for saying they're always 1, which I will absolutely do. So please don't think, despite the fact that many homework questions come out to be 1 for these, they're always 1. They're not. They're indeterminate, right? Right? So you're not going to just write down 1 all the time, right? Right. But if you're on the AP test and you're going to guess, what are you going to guess? 1. That's right. Okay. All right. Try this one on your own and see if you get the point. I still need to see that. Is it indeterminate? Work just for a second and then go into the actual solution if it's indeterminate. What'd you get? Come on. Okay, now, that's pretty much getting across all the big ideas here. You need to now just practice it a lot, concentrated practice. So, everything that's not been done needs to be done. It's your homework. Let me know if I can help you. Feel free to work together. This is all homework. There's only 9.
No, I mean, no, this is all of the.
Oh, this is all your homework, yes. Yeah, no, that's all your homework. Just do those and you're good. I'll probably just check them and get back to you tomorrow, because this is notes, and then here's the notes, so you can.
You get to take
No, but it's that awesome.
Okay, or a bunch of them. So you get this one, and then here's the first about. And then how do you get it?
How is that most of the break?
Did you enjoy it?
Oh, man. I'm not sure I'm gonna buy it, but it's, or that's what's for the school.
Yeah. I got it.
It's so good. I've read a ton of books on nature too. It's the best of the books.
250 major things in the history.
Yes, man.
You did it a bunch of times. You bet your calculus is in it. Ratio. He's had his
A little less than between gold rush and small.
Pleasure reading books.
What's one over?
Wait, this checkers? Infinity time. Checkers? Oh, yeah.